That's a 90 millisecond cold start. That's insane. That's crazy. And if we actually look at the duration of our actual handler, 142 milliseconds. So at cold start, the total duration of this Lambda function is 232 milliseconds. And this gets even better as we look at the warm starts, 4.2 milliseconds. That's including the call to DynamoDB as well. We've got 4 milliseconds as a response time from our Lambda function. That's just insane. The performance is crazy. This isn't even close to any of the other runtimes. And that's all with 128 megabytes of memory. The lowest possible memory allocation that you can give to a Lambda function. Crazy. Performance off the charts. Hello everyone, and welcome to another video on building serverless applications on AWS, and to what is the first video in a new series on building serverless applications with Rust. Now, Rust is a really fantastic fit for Lambda, and that's because Rust was initially built as a systems programming language. And since then, it's exploded, and you can build almost anything with Rust now. But its history as a systems programming language is really useful for us as serverless developers because systems programming and embedded devices are typically quite resource constrained. Now, you're probably thinking Lambda isn't resource constrained. But when the Lambda pricing model is based around the amount of memory you allocate to your function, the lower memory you can allocate, the cheaper it's going to be to run your application. Which means Rust as a language which is built for these resource light environments means we can get a lot more done with a lot less memory. That's going to improve our environmental footprint, improve the cost of our systems. And what we're going to do for this first video is just going to look at the getting started experience. We're going to create a new serverless application using the serverless application model, deploy that to AWS, and have a look at what the performance characteristics look like. Because if you haven't seen this around social media, Rust is fast. Let's get straight into it. So here I am in a terminal window now, and I'll put some links in the descriptions for getting set up and getting started, ready to do Rust development. I'm running a Windows machine here, but I actually found it easier to use the Windows subsystem for Linux, and I'm actually running within Ubuntu 22.04 here. And there's a few different things I've got installed. The first is Rust itself, and we can see that if we look, I've got Cargo installed and Rust installed. We've got the SAM CLI installed, and I've also got Cargo Lambda installed. And Cargo Lambda is an extension to the Cargo CLI that allows us to build and work with Lambda functions locally. Links in the description below to get all this set up. Now, to get started, I am going to run a SAM init command. And the SAM CLI makes it really easy for us to start building out production-ready serverless applications. And it provides a set of quick start templates that allow us to get started. So I'm going to use one of the quick start templates, and I'm just going to start with the Hello World example. We don't want to use Python, so let's select Rust, and you can see that down at the bottom there. We've got number 20 for Rust. We don't want to enable tracing, and we don't want to enable monitoring. And then we're just going to give this project a name. The name we enter here will define both the folder structure on our file system, but also the name of the Rust application that gets generated. So I'm going to call that Rust sample. So here we are now within that folder structure within Visual Studio Code. And there's a set of really great extensions for Visual Studio Code for building Rust applications. And you see, if you're a Rust developer, there's some things in here that are quite familiar. We've got our cargo.toml file where we're describing all of the crates that we have. We've also got a make file for building our application. And you can see this is using Cargo Lambda, the CLI extension, to actually build our application. And then we've got one other file in the root here, which is this template.yaml. This is a template for AWS SAM, and this is how we're actually defining our serverless resources. So let's go off and have a look at our application code now. So if I open up my main.rs file, we can actually look at the Rust code that's working here. So you see we've got our main function, it is async, and this is going to be the entry point for our Lambda function. So when Lambda is first invoked and the execution environment gets created, this is what is going to execute on initialization. So we're setting up a couple of variables and creating the SDK. So we're getting some configuration from the environment. This is things like permissions and secret keys. We're grabbing the table name for the DynamoDB table that we want to interact with. And then we're creating a DynamoDB client using that configuration that we loaded from the environment. This AWS config and this client object both come from our DynamoDB SDK create. And once we've created all of this, initialized all of these SDKs, we then actually get to setting up our runtime. So internally, Lambda has what's called the Runtime API, and it's the Runtime API that you can make HTTP requests to get the next event to be invoked. And all of this Lambda HTTP run function is doing is just abstracting that away for us. So Lambda HTTP makes it really easy to work with HTTP payloads. That could be API gateway, that could be application load balancers. And then this run function is what is actually setting up the runtime. So behind the scenes, this is going to make the API calls to the runtime API and grab the next event to be invoked. When there's an event to be passed to our Lambda function, that is then going to be passed into this closure here. And it's this bit of code here that is actually going to run for every single request. So if you think about the flow of an event through this Lambda function now, the event will come into the invoke service and it will sit and wait to be processed. This Lambda runtime is going to make a call to the internal runtime API, grab that event payload, and then pass that event payload to the closure that we've defined here. And this closure is simply passing a request off to this other put item function. This is a pretty typical pattern when you're building Lambda functions with Rust, is to have in your main function the bootstrapping of the runtime, but then your actual business logic, your actual function code, just pass that off to another function that the runtime can then call. And this put item function takes in a couple of parameters. We've got a reference to our DynamoDB client. We've got the table name itself, the DynamoDB table that we want to interact with. And then we've got the actual request that came into our function. And you see, we're only borrowing a reference to our DynamoDB client and our table name, but we're actually passing in the request, and we're going to let the put item function take ownership of the request itself because it might need to do some other things with that request. When we actually get into our put item function here, this is where we're actually interacting with DynamoDB. So we're reading the path parameters from the request that comes in. And if we have a look at this request object, you see we've got some pretty typical HTTP parameters here. We've got the body, we've got the headers, we can grab the method that was used, the payload, the query string, the path parameters, all of the typical things you'd expect from a HTTP request. In this instance, we're grabbing the ID parameter from the path parameters, and if that doesn't exist, we're going to build a 400 response with a body that says the ID is required. If we do have the ID path parameter, however, then we're actually going to grab the body itself, and the body that comes in from API Gateway could be both text or it could be binary encoded. So that's why we've got a reference here just to check that if the body is text, we're just going to grab the body. If the body is binary, then we're actually going to turn that into a string. So we've actually got a string representation of our body contents. And then all we're going to do is just going to write that to DynamoDB. So we're using the DynamoDB SDK here. We're going to use the put item API call. We specify our table name, and then we're just setting the ID of that record to be our ID from our path parameter. And we've got a second attribute on that DynamoDB item, which is the payload itself. And then we're going to send that request to Dynamo and await for the response. Based on the result of the query to DynamoDB, then we're going to match on that result. And if the response from DynamoDB is okay, then we're going to return a response to our API of status 200 with a body saying item saved. If there's an error that comes back from Dynamo, we're then going to set that error to be 500 and just say there's been an internal error. So let's just quickly recap what's going on in this Rust code. So we've got the main method that's going to be invoked at initialization time when our Lambda function execution environment is created. And that's going to set up the Lambda runtime. And the Lambda runtime is going to start polling the internal runtime API to look for new requests. When a new request comes in, this closure is then going to be called, and that request is going to be passed to our put item function, which is then going to go off, extract some data from the request itself and make a request to DynamoDB. Let's actually go off and deploy this and we can have a look at the performance of Rust. So I'm in the same directory here as my template.yaml file. And what I can first do is compile my Rust application. So I'm going to run make build. Remember, in our make file, we've got that pre-built command to use cargo lambda to build our application, and we're going to build that targeting x86 version of Linux, because on Lambda this is going to run on top of Linux. That has now finished compiling now, and you'll notice that we have got a new version in target lambda. We've got our bootstrap file there. If we looked at the properties, that will be created right now. So the next thing we can do, now that we've compiled the binary, is run the SAM deploy command, and we can pass in this guided flag, and the guided flag will take us through a wizard that will allow us to define how this application gets deployed. So let's call the app Rust demo. We want to deploy to EU West 1, which is Ireland. We don't want to confirm the changes before they deploy. We do want to allow CloudFormation to create IAM roles so that our function has a role to assume. We don't want to disable rollback. This is a really cool feature of AWS SAM in that if you define a Lambda function with an API and you don't define authorization, SAM will actually ask you to confirm that that's okay, that you're going to deploy an unauthorized API. We're absolutely fine with that. And then we do want to save these arguments to a configuration file. And what SAM's going to go off and do now is it's going to zip up that binary file and upload that to S3. And you saw that happen right there. And then it's going to go off and create the CloudFormation change set to actually deploy this application. And you get real-time feedback in your terminal window, so we can see what's happening here. These are all the things that are going to be deployed. And then we can actually see at the bottom real-time updates as this function gets deployed. So you see our DynamoDB table has now been created, and it's just in the progress of creating our IAM role. Now this first deploy can take a couple of minutes, so I'm just going to pause the video here and I'll come back in just a moment. So that has actually finished deploying now, and you see we've got some outputs here for some details about the resources that have been deployed. Importantly, we've got our actual API endpoint here. So let's grab a copy of that and go off to Postman to actually test this API. So here we are in Postman. Let's create a new request. We'll pop in that URL, and this needs to be a put request, and we've got ID of some kind. Remember, the API endpoint we're expecting is a put, and we're expecting an ID of some kind in the path parameters, and then we just need to pass in some kind of body. So let's pass in hello world, change that to JSON, and then we'll actually make this put request to API gateway, and you see that's responded, and we've got our item saved response back. If we hit this a few more times now, you can see we've got a pretty consistent double-digit millisecond response time here from our API. So let's go off to the AWS console now and actually have a look at that. So if I go into CloudWatch, let's go and have a look first at the log messages for this Lambda function. So we're in our CloudWatch log group now, and let's have a look at our single log stream. And we can see the actual log messages here from our invoke. And within the log message, we can actually see our durations and our init duration. So if we look at this very first request here, we can see that we had a cold start duration of 89 milliseconds. That's a 90 millisecond cold start. That's insane. That's crazy. And if we actually look at the duration of our actual handler, 142 milliseconds. So at cold start, the total duration of this Lambda function is 232 milliseconds. And this gets even better as we look at the warm starts, 4.2 milliseconds. That's including the call to DynamoDB as well. We've got 4 milliseconds as a response time from our Lambda function. That's just insane. The performance is crazy. This isn't even close to any of the other runtimes. And that's all with 128 megabytes of memory, the lowest possible memory allocation that you can give to a Lambda function. Crazy. Performance off the charts. And that is how simple it is to get started building serverless applications with Rust on AWS. Over the next few weeks, I'm going to dive into different event sources, how you can test your serverless applications, and some of the best practices as you start to build out more production-ready Rust-based serverless applications that might have multiple functions and little bits of shared code. As always, if you've liked this video, please like and subscribe, and I will see you all next time.